Hi, so this is week 6, Tuesday. The agenda for today is I'm going to continue on sandwich material example. Then we're going to do the last section of eccentric unsymmetrical bending. And then for those of you that have to do a term test 1 correction, it'll be done on June the 8th from 7 p.m. to 9:30 p.m. and it'll be done face to face in ETB 2 to 3. There will be no lecture on June the 8th, okay, because we have some students doing their correction for term test 1, okay. So today we're going to continue the example on sandwich material. So we are going to determine the position of the neutral axis, okay. So we did this probably close to 2 weeks ago now. So just to quickly recap, this material over here is under both axial loading and bending moment due to the uh, tilted 60 degrees from the horizontal 10 kilonewton load. So from here, what we did the last time is we determined the second moment of area, where they also determine the position of the centroid from the top. Then we did our stress. The stress, we calculate the stresses induced by axial loading. So material 1 will see 706.522 times 10 to the 3 Pascal. And stress X in material 2 is 1.359 times 10 to the 6 Pascal. So I'm going to continue on this problem. And what we're going to do is we're going to determine the position of the neutral axis. So just to recap, this is our moment. Oh, excuse me. This is the moment in Z, right? So we know that over here will be under compression. So this will be under tensile. So if you look at over here, what we have is at this end, if we know, we do know the position of our centroid, our geometric centroid. So this is just a sketch. So if this is our geometric centroid, so i.e., we found that from the top, right, this position is 123.207 times 10 to the power minus 3 meters. And due to bending moment, we know that over here will be under compression, and at the top will be under tensile. Okay. So what we're going to do now is we're going to determine the position of the neutral axis. Okay. So we're going to determine position of the neutral axis. And as you can see, the neutral axis, right, will be in material 2. Okay, so for material number 2. Okay, so we have to find maximum tensile stress in material number 2. So we know that stress X of material number 2 in terms of tensile, so it'll be equal to 1.359 times 10 to the power 6. And we know it's with tensile plus Yn mz over Izz multiplied by y. Why this value is over here? Because this is due to the, okay, so over here, this is due to the axial load or axial force. And this one over here is due to bending moment. Okay, that is due to bending moment. So we know we did calculate our moment in Z before, and we do have our IZZ. Okay, so this will be equal to 1.359 times 10 to the power 6. And then we did pick our reference material to be what? Our reference material to be I think material 1 was our reference material. Okay, so maximum tensile. So this will be plus, and then this will be equal to 200 over 104, and then we're going to multiply by 17.936. That's our moment in Z, times 10 to the power 3. And then we're going to divide by our IZZ, which is 65.694 times 10 to the power minus 6. And then over here, we are going to multiply by, so this is the position of the max, sorry, not over there, I do apologize. So this is the position, okay, which I'm shading in red now, where you will have bending moment inducing tensile stress. Okay. So from here, we need to find that position. So this is equal to 123.207 times 10 to the power minus 3 minus. So this thickness over here, we know is 10 millimeters. Okay, minus by 10 times 10 to the power minus 3. Okay, so this whole thing over here. So this will be equal to 1.359 times 10 to the power 6 plus, let me take out my calculator, 123.207 power minus 3 minus 10 power minus 3 times 17.936 power 6 power 3 divided by 65.694 power minus 6 times by 200 divided by 104. So this will be equal to 59.438 times 10 to the power 6. Let me do it again. 123.207 power minus 3 times 17.936 power 3 divided by 65.694 power minus 6 times by 200 divided by 104. Yep, 59.4 39.438. So this will give us a stress maximum tensile of 60.797 times 10 to the power 6 Pascal. Okay, so this is the maximum tensile for material number 2. 60.797. So next, we still have to determine the maximum maximum compressive stress. In material 1 and material 2. Okay. So from here, stress X, material 2. So this will be equal to positive 1 point. Why this is positive? Because the axial load is always inducing tensile residual stress. Then plus by 200 over 104. Oh, sorry, minus now because it's a maximum compression. Minus by 200 over 104 multiplied. So the moment did not change. And then the second moment of area did not change. So the only thing that changed now is we want to find this distance. Okay, so I'm going to change the color now. So this dot over here. So what we are aware, we know the distance from here to here. We know that that is equal to 123.207 times 10 to the power minus 3 meters. Okay, so now we want to find this position, the distance from here to here. Okay, so we just need to take 300 minus by 123.207. Okay, so this will be equal to 0.3 minus by 123.207 times 10 to the power minus 3. Okay, so this is equal to 1.359 times 10 to the power 6 minus 0.3.207 minus 3 times by 17.936 power 3 divided by 65.694 power minus 6 times 200 divided by 104. 92.824 times 10 to the power 6. Let me do it again. 0.3 minus 123.207 power minus 3 times by. Oh no, hold on. 0.3 minus 123.207 power minus 3 times by 17.936 power 3 divided by 65.694 power minus 6 200 divided by 104. Yep, 92.284. So this will give us 91.465 times 10 to the power 6 Pascal. Now, so the next thing is we are going to, so we find these values already, which will help us locate the position of the neutral axis, or we can use the formula. We directly use the formula. Let me elaborate what do I mean by that. Okay, so we know at the neutral axis, right? We know at the neutral axis, stress X for material number 2 must be equal to 0. Okay, we know that for a fact. So if we look at stress X formula, okay, for material number 2, we know that this is equal to Px over A1 E1 divided by E2 plus by A2. And then we know that there's a minus over here, N2 Mz over Izzy. Okay. So now at the neutral axis, this whole thing is equal to 0. So if I rewrite equation number 1, right, we have Px over A1 E1 over E2 plus by A2, and this will be equal to N2 Mz over Izzy. Okay. So now we want to find the position of y. Okay, we are going to find y. Okay, we're going to determine y from equation number 2, right? So we know that the stress over here is 1.359, right? So if on the left hand side is 1.359, you bring over is minus 1.359 times 10 to the power 6. And then N2 is equal to 200 divided by 104. right? And then you have your